everybody. We have the pleasure to have here today Professor Alfio Quarteroni, who is one of the most prominent mathematicians in the world. Alfio comes from the Italian school of Pavia, a very famous school beyond Magenes on PDEs, and in particular on numerical methods for PDEs. And he made an extraordinary career. Now he is a professor at Politecnico di Milano, he is director of MOX, and is also professor emeritus at EPFL in Lausanne. And the list of awards and prizes that he get, I would read it in 15 minutes, so I will not. I will just say a couple of things. In particular, he had the ability, the great capability of transferring very deep and complicated mathematics and transfer this to applications. Let me mention just two. One is the one he will speak today, and in particular, his big group, is in contact with the most important hospitals, for example, in Lombardia. He has a very, very strong connection with medical doctors that makes use of the software developed at MOX. And also other ones. Let me quote one, because I remember that with interest. One morning I woke up and I saw Alfio Quarteroni in Gazzetta dello Sport. And then then this was related to the fact that he has worked to a project for the simulation of the boat Alinghi, when Alinghi, the Swiss boat, won the America's Cup for the first time against the usual winners, which were New Zealand and American one. And they made use, and this was considered the real secret of Alinghi, they made use of the software developed by Alfio and this group to optimally simulate the interaction between the boat and, of course, the wind and the water. And this was certainly one of the great application, in this case to sports, that he had the ability to create. He has been recently a recipient of an advanced grant, an advanced ERC grant, which is still active on these topics. And this is the last thing I mentioned, then I leave him the stage because I don't want to subtract time to him. It's the first time that an applied mathematician is part of the committee that assigns the Fields Medal, and this has happened last time, and the applied mathematician is Alfio Quarteroni. So with this, I conclude, and I leave you the stage.
So thank you very much, Nicola, for this very nice introduction, and thanks GSSI for inviting me. It's a pleasure and an honor to be here. So this is the title, Mathematical Art. What is a mathematical art? Well, let me just start by the end instead of starting from the beginning, as we typically do. This is what we are supposed to achieve. We are supposed to achieve, but we do not achieve. So I don't know why it does not go on. What's happening here? It used to work until a few minutes ago.
Maybe.
So this is going to be a talk on the mathematical art. And let me start from the end. This is what we're going to achieve at the end, okay? Just to give an idea. So it's not an artificial art, it's a mathematical art, meaning that you have here a heart, say a human heart, which is beating, and is beating as, say, realistically, as a human heart could beat. And in particular, we are interested in providing not only a qualitative behavior, but also a quantitative behavior. What you see on the left is a map with a millivolt. So it's the propagation identical field on the heart during a heartbeat. In the middle, you see the displacement. And the scale, you go from 0 up to 2 centimeters. out of, roughly speaking, 8 centimeters of diameter. So this is a big deal, it's order of 25%. So it's a large displacement. And on the right-hand side, you see what's going on within the 4 chambers, in the 2 atria and the 2 ventricles. And you have the blood flowing from the pulmonary vein. So this is the oxygenated blood from the pulmonary vein to the left atrium, and then through this valve, which is the mitral valve, we'll see it again later, into the left ventricle. And then when this squeezes in the so-called diastolic phase, it will be ejected into the aorta, the ascending aorta. Right. So those are 3 different physical quantities that we can reproduce realistically. When I say realistically, I mean that the values are correct values, or say in the range of correct values. And since I'm talking to an audience which is made of most of mathematicians, let me say that it takes order of 1 to get qualitative results, and order of 4, so 4 times to get real results. So when you have to make the fine-tuning, this is really very, very costly in terms of mathematical development. So if you really want to achieve real results, I mean physiological results, then really they have to strive. So I'd like to give an idea on how to get there. The idea is that we are motivated by clinical problems. And then when we focus on a clinical problem, we have the so-called pre-processing. Before using the mathematical models, we have to go from data, clinical data, to shapes. Then we have the mathematical model. Then you have to solve it numerically, because those equations are not solvable by paper and pencil. They are too complicated, of course. And then you have to address the original problem, provide results, and of course validate these results, make sure that these results are correct. So this is the complete roadmap, say. So let me go through all these steps. Clinical problems, which kind of clinical problems are we able to treat until now? Well, these are examples. We start from coronary artery diseases to dysfunctions of the valves, of some of the valves, to the treatment of, say, aortic aneurysms, to the treatment of disturbances in the rhythm, like arrhythmia or tachycardia or ventricular fibrillation, say, then cardiomyopathies, and generally speaking, heart failures. And recently we have also been considering the impact that some COVID infection might have on the cardiac function, say. So those are titles. And for each title, we have been doing something with some specific, say, clinical counterpart. Now, what is the pre-processing? Pre-processing is something that typically mathematicians do not like and that do not go through, but they are very important. You have to start from clinical data from patients, and you have to construct shapes, and then a grid in order to solve the problem. And then, for instance, in this case, to reconstruct the fiber distributions, which is in general not provided by clinical data completely. And this is what you have to do before starting with the mathematical model. So we start from, for instance, CT scans or MRI, late gadolinium MRI or phase contrast MRI, which are typical, say, exams that are taken. And this is, for instance, the way we are using all this data. We use CT scan typically to generate the shape for ventricle and coronaries. We use cine MRI to generate shape and motion, external motion. LGE MRI to identify zones where you have scars. For instance, because there has been a, say, heart attack or an infarct, and then you have regions that are not conducting the electrical signal as they used to do. And we use phase contact MRI to generate boundary conditions. Boundary conditions are very important mathematically because you need them to solve the problem. One issue which is very important is the generation of the fibers, the cardiac fibers. Now, the fibers are important because, well, let me just oversimplify very complex concepts here, right? They are important because, in particular, they allow the conduction of the electrical signal. So they are the roots through which the electrical signal is propagated. And on the other side, they are important because they guarantee the torsion of the heart, they allow the heart to have torsions, and therefore to the systolic phase in particular to eject blood. So they have an importance in the mechanical model and then in the electrical model. So how do we generate the fibers? Typically, you do not have them from images, unless you have a diffusion tensor MRI in your lab. But even in that case, which is very costly, so it's not yet routine. But even in this case, the images may be very blurred. So it might seem a paradox, but we are using partial differential equations to generate missing data in this case. Usually you use data to feed partial differential equations in mathematical models, but in this case, we are using partial differential equations to generate the missing data. I'm not going through this analysis, but this is the name that is used in this case, the Laplace-Dirichlet rule-based. Laplace is because we are using we solve Laplace equations to generate the bundle of fibers and then the fibers. So this is the pre-processing, very quickly explained. Then we have the modeling. Now, modeling is the central part of the story. What does that mean, modeling? Well, it means that we try to use mathematical equations to represent physical processes, those that occur in the heart. So which kind of physical processes? Well, here you see the names, right? First of all, electrophysiology. What is responsible for generating the electrical field? Then you have force generation. At the level of every single cardiomyocyte, you have the generation of an active force, which is due to the presence of the electrical field. Then you have the mechanics at the global scale, namely the model that allows the heart to dilate and to relax and to contract. Then we have the fluid dynamics, because we have blood flow in the four chambers, in the two atria and in the two ventricles. Then we have the coronaries that perfuse the myocardium with blood and oxygen and nutrients. And then you have the circulation, the external circulation, because blood is not in the middle of nowhere. Heart is not in the middle of nowhere. It's in the middle of the circulation, right? And if you want to reconstruct the ECG, the electrocardiogram numerically, you have to account also for the conduction in the torso, not only in the heart, but also in the torso. So all those, balls contain indeed a physical process that occur in the heart. And the beauty of this organ is that all these elements are interacting together. So it's going to be a couple problem, mathematically speaking. And of course, no linear problem, because there is very little, very few linearities in our life, right? So in general, our life is non-linear, in particular biological life. So a mathematical model of the heart should in principle be able to account for all these processes together. So let me go through them, even if I'm going through quickly without insisting, right? But just to give you an idea of the problem. First of all, at every single cell, we have channels. We call them the ionic channels that open and close. When they open, because the cells are stimulated by the electrical stimuli, when they open, they allow ions of calcium, and potassium, phosphorus to go back and forth, right? And this creates basically a delta potential. So you create a force that is generated at the cell level, and say in a very rough way, every single cell or cardiomyocyte, say, then in the end will contract or dilate. So create a kind of train of waves that propagate, and in the very end, this will provide you the mechanical behavior of the whole organ. So these ionic models are described by system of ordinary differential equations. For every single cell, you have a system of ordinary differential equations that change in time of that type. So you need something which is biophysically detailed to reproduce in particular the calcium dynamics, because calcium is the main trigger of the deformation of the cells, of the deformation of the cardiomyocytes. Now, you have different models depending upon where you are. If you are in the ventricles, if you are in the atria, if you are in the septum, you have different type of mathematical models. You have to think that for every second, you have this type of picture that describe what is called the action potential. You have a depolarization and then early repolarization. So this takes place in the order, as you see here, of say 400 milliseconds for every heartbeat. So you have this kind of these continuous waves that are propagated, that are generated, and you have to catch them correctly with the mathematical model, say. Then you have the electrophysiology. What is the electrophysiology? Well, it's the process that allows you to generate the electrical field that propagates first in the upper part of the heart, in the atria, and then in the lower part of the heart. So at every single instant of our life, you have a stimuli that is generated at the sinoatrial node in the upper part of the right heart. And this stimuli is propagating then in the upper part of the heart and then down to the lower part of the heart. So the system, the mathematical system that is behind this type of process is called, say, the bidomain model, the bidomain method. It is a bidomain method because you are basically, well, that's a bit difficult to explain, but you're obtaining these equations by kind of upscaling, moving from the micro scale to the macro scale by an homogenization process. So the result of this is, if you solve this equation, you have V and VE. V is the transmembrane potential, and VE is the extracellular potential. And as you see, this is, if you are a bit, say, acquainted with partial differential equations, this is a system of reaction diffusion equations of nonlinear type, and which is coupled to the system of differential equations that I've been considering before, which is responsible for the ionic propagation, say. You need to account for the generation of this active force at the cell levels. And this is because the cardiac cells are excitable, which is very important. So here you need to go at the level of every single cell, and I'm not going to develop this point, but you easily end up with this gigantic system of equations, which are unaffordable. So you have to see the way you can reduce them. And this is a way that we proposed a few years ago to reduce this system in a way that is still physically reasonable. So we are in the framework of the so-called active stress. We are generated the say the length of the sarcomere, and we are simulating the Frank-Starling mechanism. The Frank-Starling mechanism is the one that explains the ability of the heart to change its force of contraction in response to changes in the venous system. So we try to be as, say, phenomenological consistent as possible in generating this force. Then you have the macroscopic mechanical model, the one that is responsible for the passive mechanics. If you take any object, any, say, amorphous object, and you apply a force, then you will have a reaction in the form of deformation. So this is true also for the heart, and this is responsible for, say, this system is the one that allows you to compute D, which is the displacement. The displacement in every point, X, Y, Z, and for every time will tell you the way that specific point in the heart will move in the process, in the systolic and diastolic process over the complete heartbeat. Well, this is just for mathematical amateur, right? In general, when you solve a PDE, you take any book, any textbook, and you say, okay, consider this PDE and take these boundary conditions. So who provides us the boundary conditions in the heart? No one, nobody. You cannot pretend asking doctors to make invasive exams to provide you boundary conditions. So you have to guess the boundary conditions. And when you guess the boundary conditions, you have to be consistent with the physics. Otherwise, what you'll get will be garbage at the end. So you have to develop new kind of boundary conditions to provide a realistic environmental context for your heart. Then you have the fluid dynamics. So within the chambers, you have blood flow, which is strongly stimulated by the fact that the heart is contracting and relaxing, right? So blood is subject to very important forces, external forces, say. So what you see here is just a detail in the atrium, in the left atrium, what's going on. So we use the Navier-Stokes equations. Navier-Stokes equations are equations for incompressible viscous fluids. And they're expressed in terms of two variables. One is the velocity, which is called here u. U is the flow velocity. So u of xt tells you at any point x in the three-dimensional space at time t, which is the velocity of that particle, say, flow particle, and then the pressure. So we have the Navier-Stokes equations in a domain that is moving, that is changing in time. So we have to resort to a very special form of Navier-Stokes equations. We call it arbitrary Lagrangian Eulerian form. You need to recover at every instant the actual volume of the domain, of the region. So you need an extra equation, which is an elliptic equation. Now, in physiological conditions, in the heart rhythm, blood is not turbulent. It's basically in permanent transition toward turbulence, which is even more difficult from the mathematical viewpoint, from the numerical viewpoint. Okay. So what we are using here is what is called a variational multiscale model with a large eddy simulation to try to capture the dynamics of the vortex dynamics of blood, say. We have valves. The valves are tiny objects that open and close very quickly. And you have different ways to model them. You can either model them by three-dimensional models or try to simulate their presence geometrically, which is what we do here. So we add an extra term to the momentum equation of Navier-Stokes. And this extra term basically contains a delta Dirac function, which is generated by the difference of velocity between the velocity of deformation of the rate of deformation of the valve and the external flow field. So we are further modifying the Navier-Stokes equations with this type of approach. And then we have the perfusion. What is the perfusion? Well, we suck blood from the ascending aorta and you bring it to the coronaries. The coronaries are there to nurture our heart, to bring blood to the myocardium and oxygen to the myocardium. And coronaries, typically, we see the major coronaries. And those are actually reconstructible from clinical images. You go down to the level of 1 millimeter, and typically you cannot go further down. So those are the coronaries that are called the epicardium coronaries. They are sitting in the external part of the heart. But then they bifurcate and bifurcate and bifurcate, and they generate a bed of coronaries, which enter into the myocardium, and which are becoming, finer and finer. So we use a method that makes use of about 80,000 small coronaries, and we use a multi-scale method, which treat this coronary bed as a porous media flow, as a porous media, say. And we have 3 levels of porosity and permeability, and we combine this with the Navier-Stokes equation that we use for the epicardial coronaries. So it's a multi-scale problem for the perfusion, say. Now, I told you that heart is not in the middle of nowhere, is embedded into the external circulation, but the external circulation is made of hundreds of large arteries, billions of capillaries. So you cannot pretend using fluid dynamics in 3D to solve all this complexity. So what we do is using the analogy with electrical circuits for the external circulation. In technical terms, you say that we use a zero-dimensional model. 0D because you don't have space dimension any longer, you just have time variability. So we have all these previous models for the heart coupled to the external circulation. And it's a closed loop, of course, with a feedback. Then we want to compute the numerical electrocardiograms. So we have the electric potential that is generated on the surface of the heart, the epicardium, which is coupled to a diffusion problem in the torso that bring this potential, this electrical field on our chest, where we have the electrodes. Right? So we generate the ECG numerically in this case. And this is, fortunately, the end of the story. right? So this is the model. Now you see a synthetic picture of all the physics that are encoded into the models, and you have seen the equations before. So this is the master problem that you have. And this is the mathematical heart, say. With all these connections, all these physical processes are actually exchanging physical informations. So it's a kind of holistic view of the heart function, say. Now, you go to the numerics. I'll be extremely quick. Actually, I'd say almost nothing about the numerics, but this is my field. So this is where you actually, I mean, been introducing most of the originality. And so I will skip all the numerical part. But let me just say that we develop our own software completely. Now we use what we call LifeX. And LifeX has today about 15 developers at MOX in Milano. There are about 150 users around the world. And well, this is a pessimistic estimate. Now it's about 150,000 lines of code. And this is a research code, say, which is there to allow us to solve the problem. And when you solve the problem, we have to use proper algorithms. And now I'd like to make a comment. What you've seen until now is what is typically called the physics-based model. Namely, we start from physical knowledge and we try to develop equations, right? But now I'm going to couple it with artificial intelligence. Why that? Because it's very fashionable from one side, but actually because it is a need. So we started 5 years ago with this project and there was nothing about artificial intelligence. And now today it's difficult to see a single piece where we are not using in a way or another machine learning algorithms together with the physics-based, not alternatively, okay? And I'd like to give you, let me just say something which is very general because this is a colloquium, so it's not necessarily only technical. Let's say that philosophically speaking, in the 20th century, we had 3 pillars for science, right? There were theory, experiments, and numerical simulation. And to produce excellent science, at least if you are in the computational business, you have to be good in all these 3 pillars, say. Now, today, we have a 4th pillar, right? Which are the big data. And you know, we have data everywhere. And the point is how to take advantage of that, right? So there are 2, dogmatically speaking, 2 approaches that are alternative one to another. The upper one is the one that I've been talking about until now, using the minimum set of data that you need to feed your partial differential equations, which is the model, and then finding the solution. The one below is one where you basically do not consider any physical law, any knowledge, but you just use data to train a network, for instance, an artificial neural network, and then, of course, try to use it to produce solutions or output of solutions. But in fact, what we are doing is putting ourselves at the interface between the 2. This because it's indeed a cooperative game. It's not an alternative game. You have these 2 drops that can actually interact a lot with one another in many different ways, right? And so these are many different strategies to try to have these 2 worlds interacting one another. So we're basically combining or coupling the physics-based knowledge with data-driven knowledge. And why do we do that? Well, we do that because we are motivated to do that. And here are a few examples. And I'll go very quick on that. The first example is that the physical law that generates the active force at the cardiomyocyte level is not known. So there is a lack of knowledge. So we use artificial neural network to learn this law, not because in the end, the artificial neural network will tell us that this is the law written, right? Like as F equal to MA. No, this is not yet possible for artificial neural networks, but artificial neural networks can be used to generate input-output relationship. For every single input, you change the input, you use it, and you get a new output, right? So use artificial neural network in this case to learn the dynamics of the force generation at the cardiomyocyte level. And when I say learn, again, I do not pretend learning the law. That would be too much. But learning the data to solution map. So every time we have to reuse it. If you have this F equal to MA, this is a law that is applicable to every possible system, right? This is not the case. We're just learning the law, not explicitly, but the action of the law on any specific circumstances. This is one example. This is another example. When we have to solve our ionic models, we are at the cell level, we have many parameters that enter into the ionic models. How many? Well, it depends on the model. You can go from 2 to a few hundred. How do you understand? How do you decide which parameters we are going to use? Again, we use, in this case, what we call a multi-fidelity PIN. PIN stands for Physics Informed Neural Network, to estimate these parameters. This is another example, another use. When we solve our problem, it will take forever. We'll show you later on the characteristic time. So in particular, the three-dimensional part, say a single ventricle, is extremely expensive. We want to replace it by zero-dimensional ventricle description, which is very quick. So we are simplifying the model at the, say, at the ventricle level to compute, for instance, in this case, the PV loops. PV loops are those diagrams that you see up there, and doctors know them very well. So you see this curve, it's kind of hysteresis curve, which describes the relation between the pressure of blood in a ventricle and the volume, right? And those are very important curves. So we use these zero-dimensional models to learn these PV loops thanks to neural networks, say. We do the same for the electromechanics, for the combination between the electrophysiology and the mechanics. Every time we change the type of neural networks, the type of mathematical approach, we use them to express the global sensitivity analysis. What is the sensitivity analysis? You have in such a big model many parameters which have a physical meaning. You see them on the left-hand side, on the rows, right? And then you have different outputs. And you want to see the way the different outputs, all of them with a physical significance, will be sensitive to the variation of the physical of the parameter, the input, say. So you use Bayesian analysis to that. And again, we use artificial neural network to learn the sensitivity of the different parameters, and so on and so forth. We use them to generate or reduce order models to compute the complete manifold of solution when you change different parameters. We use them to solve the inverse problem of electrophysiology. What is the inverse problem of electrophysiology? If you go to a hospital, maybe they put electrodes on you, you compute the ECG, and the doctor is interested in the retrieving the behavior inside the heart. So mathematically speaking, this is, and maybe finding what's going wrong in the heart, right? Mathematically speaking, this is an inverse problem. You see the boundary condition, and you have to retrieve, say, the solution of the interior. That's very difficult. Solving inverse problems is much more difficult than solving direct problems. And again, we use artificial neural network to help, all the time combined with physics-based models, say. Let me, if I still have some time, all right, let me give you an idea of the type of result that we can achieve. Now we have seen more or less the methodology. Well, we can compute the electrophysiology in the heart. What's that? What you see here is in the middle picture, you see on the map, which is especially in terms of millivolt, in the ventricle go from -80 to 40. -80 is blue, 40 is red, and in the atria we go from -80 to 20. And you see the way the electrical field propagates. It starts in this very point up there. This is the sinoatrial node, and it propagates first of all in the atria. Then there is the atrioventricular node, which is a gate. And when the atria are completely activated electrically, then the signal passes on the lower part of the heart. And what you see on the left-hand side is a picture that doctors know very well. Those are the isoline of the activation time. So a line is joining points that are electrically activated at the same time. This is in sinus rhythm, so for a heart which is working properly, say. And you see the same on the right-hand side, right? The electric front that propagates in the heart. To obtain these results, you have to solve the electrophysiology model, which is a subset of the whole model. Then you couple it with the mechanics, and then you solve the mechanical deformation. You go for the mechanical deformation of the heart, right? What is very important to notice is that the results that you obtain are in the range of acceptable results. You compare with the literature, and you see that we are in a, say, good range of accuracy. This is extremely important because it's very easy to generate results that have nothing to see with the reality. I mean, qualitatively speaking, they look the same, but then when you talk to doctors, you see that they have nothing to see with the reality. And it's extremely difficult to find realistic results with a model with this complexity. This is the heart that is beating in the chest, and what you see here is the TAV is the active tension at the cell level. Remember, the active tension is the one that is generated at the cell level due to the presence of the electrical field. What you see here is the same picture for a different heart. And what you can notice is that in this specific case, you go from 0 to 1.6 centimeters. So this maximum displacement of this heart is 1.6 centimeters. So it's a big displacement. It's what is called a large displacement. This is the fluid dynamics. This is the left, so-called left heart. You see in the middle of the picture, you see the pressure, the values of the pressure. We go from 0 up to 120 millimeters of mercury. On the left-hand side, we see the intensity of the velocity field. We go from 0 up to 1 meter per second, which is a high speed, I would say. A meter per second is order of 36 kilometers per hour. And what we see on the right-hand side is the formation of the vortices. So it's not a turbulent flow in this case, but something that tends to, say, is in transition to turbulence, say. Here you have the complete picture. You see the fluid dynamics in motion. You see the valves, the two valves in particular. This is the mitral valve, and this is actually there are four valves. So this is the mitral valve, this is the aortic valve that feed the aorta, and this is the pulmonary valve that allows to connect the right ventricle to the pulmonary artery, bringing venous blood to the lungs. And now what I would like to do is to give you an idea of the clinical applications. So far, what you have seen is the setup of the model. It's numerical verification through examples. And now I want to give you an idea of the type of use that you can make, which has a clinical relevance. So this is something that we carry out with the San Raffaele Hospital and Humanitas Hospital in Milan. And we try to understand which is the mechanism behind atrial fibrillation, which is a very severe disease. So we are very proud to say that one of the doctors who is now the chief of division in Humanitas, and he used to be at San Raffaele until a few months ago, is using the algorithm in real time with patients to see the way to ablate the different portion of the heart in case of fibrillation. This is with Johns Hopkins University. The question is, tachycardia and fibrillation, still pathologies in the rhythm, can be better simulated mathematically only on the basis of electrophysiology models, or if you use the electromechanical model, which accounts for the deformation of the heart, you can actually end up with results that are more reliable. So we are able to prove that if you use the electromechanical model, instead of the simpler, say, electrophysiology model, you have a much better information on rise of fibrillation. This is the so-called hypertrophic cardiomyopathy. You know that the two chambers, the ventricle, left and right ventricle, are separated by the septum. And sometimes the septum becomes too thick. And if it's becoming too thick, it tends to occupy the regions which should be occupied by the aortic valve, the one that allows blood to enter into the aorta. So in this case, the aortic valve is not working properly because one of the leaflets are partly obstructed by the presence of this cardiomyopathy. So in this case, one possibility is go through surgery and cut a portion of the septum. But where should you cut and for how much? So we use our mathematical model to understand what is the quote optimal shape of the cut, where to cut in order to guarantee the maximum efficiency afterwards. And this is with the Ospedale Sacco in Milano. This is TAVI. TAVI today is very popular, is a low invasive way to insert aortic valve. It's called the transcatheter aortic valve implantation. We tried to, using our mathematical model, we tried to predict the efficiency in terms of flow field after the implant. And we developed some indicators before the implantation to guide doctors and get a better prediction of the outcome of the operation. This is with the Monzino, which is another hospital in Milano. Sorry, I'm quoting many hospitals in Milano, but this is because we, as I was saying before, we don't have a faculty of medicine in our university. I'm working at the Politecnico Milano, so it's very important for us to have connection doctors, and of course, doctors are somehow nearby. Now, this is also very funny. Maybe some of you, I'm not talking to young people, have experienced the fact that sometimes you have some problems and you go to a hospital in the cardiology division and they put you on a cyclet. And you try to make an effort, right, to try to see the way your heart is reacting. And of course, they are switching on with the intensity of the effort. And they do not have to exaggerate, because if they exaggerate, maybe you're going to stay there for the rest of your life, say. So now there is a modern way to do that. You still use the cyclet, but you inject a substance, and then they take an echocardiography meanwhile. So this is a bit poisoning, inevitably, right? So they came to us and they say, can you create a mathematical cyclet? Actually, to do it virtually, right? So can we predict the perfusion of the coronaries by simulating the cyclet mathematically? And so this is what we did. And then we have so far 9 patients. For these 9 patients, we have both the mathematical cyclet and the real cyclet. And we have been reconstructing the perfusion, the perfusion areas. And in this case, of course, this is not a theorem, this is not a proof of nothing, but it's just a remark. We are able to stay within the 2% of accuracy, 2% of error in terms of concentration of oxygen provided by the coronary, say, and so on and so forth. So I think my time is over, and I'm going to stop here. And if you have questions, I'll be glad to answer your questions. And those are the people who are actually doing the work, as usual. E qui, here it is.
Yeah, now it works. The curiosity is the following: all these machine learning approaches that you are using are, it's very, very, very interesting. First of all, what you did, it's really what all together they did, it's really incredible. The question is I mean, it is needed a lot of phenomenology, no, to train this kind of algorithms from one side. On the other side, of course, this is a case in which the phenomenology means working on human beings, or
yep.
I don't know, using this kind of stuff. So this is, it seems to me, an issue. How you can be so sure that what you are using to train your algorithm is really what should be used?
Yep, that's a very important point. You see, when you talk about artificial neural network, this is because you typically accompany this statement with big data. So many data and you want to train your network. Here, you have scarcity of data. That's a very important point. You cannot pretend having a, say, cohort of 100 patients that undergo tests just to feed the neural network. So you have scarcity of data. So what we typically do, not always, but often, is to use the mathematical models to provide synthetic data for training. And that's very classical. So we are using our mathematical models in case where you can trust them to generate data to train the neural networks. When we do not have enough data to train them, enough, say, biological data taken from people. But this is a real issue.
Ready to go? Yes. So you mentioned the problem somehow opposite of overfitting, in the sense that somehow you could generate, or having in certain moment too many data to overtrain your neural network. So how in this interplay between the physics model, the PD based model, and the machine learning, you somehow take into account the risk of overfitting the training, which could generate fake reality?
Yeah, so overfitting is one issue, and convergence of the stochastic minimization algorithms is another issue. So the training of the neural network, it creates a lot of, it's not easy in this case, when you treat real data. It's not easy to have convergence of the minimization algorithms because you have so many parameters and hyperparameters, and the issue of overfitting or underfitting is extremely important. This is sensitivity that you have to develop. So you don't have a you don't have a mathematical rule, say.
No, because you know, there is the risk of what they call glassy states that can somehow detour you from.
Yeah, well, this is true. On the other hand, you have the so-called biomarkers. So you know that at least when you are treating a physiological heart, a heart that is, say, working in a correct way, which is what we did at the very beginning. So I didn't have the time to mention this, but my philosophy is that, so why is this useful? Why is this important? What is my point of view? Then I come to your question. My point of view is that there are two different instances. One is pure science, right? Why would you need such a complex mathematical model? Because I want to better understand physiology, better than the doctors. I want to create a kind of virtual atlas, which is dynamical, predictive, and quantitative, and help the doctor for that. This is physiology, understanding physiology. And when you want to understand physiology, we need the whole machinery. Okay. When you have pathological events, you do not necessarily need the whole machinery. If you have a problem with the heart rhythm, the fluid dynamics in general is essentially irrelevant, practically speaking. And if you have the perfusion, the electrical behavior at the cell levels is essentially irrelevant. So we extract pieces of the whole model to focus on specific things. Now, when you do that, it is because we have, and this is for the clinical application, right? So we have a transversal development of knowledge, and then we have the vertical pointing to specific requests. And when we are doing that, our counterpart knows the problem. They know what they are expecting, either because they measure or because they know what they should expect in specific circumstances. So they know what are the biomarkers, they're called biomarkers, which are some, say, objective quantities to check. And this is guiding us. If you don't have this type of guide, you are in the middle of nowhere. So you are producing mathematics, but who care about that?
Yes, sorry, Alfio. So I have two questions, but they are rather connected. One is that, you know, modeling is to some extent is a standard, let's say, a standard model. I mean, general law that we are assuming work in general, but actually human beings are very personalized, even in their physiology, no? So my first question is, how do you account for the personalization either in the human being characteristics or problems that each one of us may have, no, against the standard model? And so if you have a configuration phase or something like that, and on the other side, how do you think we can actually go towards one-to-one model? So really, which seems to me where personalized medicine is going to some extent, no?
Okay, I think we are very far from personalized medicine in general. However, if we are a bit more modest, then we can already play some role, say. If you take this picture, this is rather impressive, or if you wish, scaring, right? Because those are, on the left-hand side, those are all on the rows, all the coefficients that enter in the model. And on the upper part, the columns are the outputs that have a medical relevance. So doctors live on columns and modelers live on the rows, right? So we are trying to finding through sensitivity analysis what counts for what, right? Now, when you are addressing a specific problem, then with a specific patient, then this patient will have a problem with coronaries or a problem with, say, the valves, or a problem with arrhythmia and so on and so forth. So we are restricting. You look at that specific output and you see which are the input that are more relevant. And in that case, if you really want to go personalized, you have to use parameter identification through measurements. So either you have measurements or you are lost. So, I mean, mathematically speaking, you know how to set the framework. Practically speaking, either you have extra data or everything is virtual. But in the future,
you cannot have a supercomputer in any medical office.
no.
And so you cannot repeat. At the end, you have to extract something that goes on a desktop computer. Or
Okay, this is another very important point.
But somehow related with this.
Sorry?
Somehow related.
Yeah. So yes, what is the final goal of that? First of all, well, there are different layers, right, in this business. The very first layer, let's start from, say, from academy to clinics, right? Let's stay in the academy. In the academy, the more you know, the richer your model, the better. We are scientists. We want to understand processes, right? And the more physics, the more mathematics you put in our model, the happier you are, irrespective of the cost. So just to give you an idea of the cost, we are using a three-dimensional analysis on arbitrary grids, arbitrary geometries. To simulate a heartbeat, it takes, roughly speaking, 2 days on a big supercomputer with about 2,000 cores. Okay, 2 days. It costs 2,000 euros. It's 35 kilos of CO2 that is produced, and an immense amount of electrical energy that is consumed. So it's not green. Mathematics is not green. Okay. So this is offline. This is for the purpose of understanding basic things. This is one issue. And then you are online clinics. You want to provide answers. Sometimes in real time, but this is not strictly necessary. If you are a doctor and he has to decide a therapy or the surgical intervention, he's not doing that in real time. He might do it the next day or the next week in general. Of course, if it's an urgency, then you are not using mathematics. You just have to save life, right? But if you have to plan, then you have sometimes. So you need methods that are more efficient than those that you are using in the academy. So you need to simplify. How do you simplify? Well, you can use, for instance, artificial neural networks to construct reduced order models. And it can work in the cloud. You don't have to have a supercomputer there. You need to have a program, hopefully a physicist or a mathematician or a computational scientist, just as you have in radiology, right? To better understand what's going on and to launch your program and to be able to interpret this. So I will not see that, but say in 10 years, 20 years, 30 years, the MRI machine, the CT scan will have embedded programs like this to provide geometries and biomarkers. This is not realistic. This is just a matter of having the technology, which is powerful enough. But here we're preparing the ideas. I mean, what is behind, say. That's my personal viewpoint.
Questions?
Francesco.
If you don't mind, just a question, not about general methodology, but just about one small detail of the application. How the efficiency of the algorithm depends on the way of surface modeling. So because in the
surface modeling, you mean?
Surface modeling, because you mentioned that if you model the surface, for example.
All right. Okay.
Yes, and there are several methods, and what kind of
good question. How sensitive is the numerical solution to errors on the representation of the computational domain, right? Okay. So what is the accuracy, first of all, today with the current machines? You go, roughly speaking, to the level of a millimeter. You don't go below a millimeter of precision when you have your rough data from clinical images. So you start from there, and you have to reconstruct surfaces. So you have to count that the errors that are induced there are of the order of, geometrically speaking, a few millimeters. So how does your solution, mathematical solution, even before the numerical solution, depend on this inaccuracy? Very difficult to answer. You need a priori error estimates on PD books from geometrical data. Very, very difficult to answer, because the way the wave propagation depend is not the way the mechanical deformation depend on the geometry and again fluid dynamics. So that's very difficult. So what I want to say here again is that I personally, I do not pretend providing results that are 1%, 2%, not even 10% accurate. I cannot guarantee that. It's so complex that I cannot guarantee that. the theory, the mathematical theory, will help us progressively to improve this knowledge. But doctors very often decide on the basis of deciding this protocol or that protocol or that protocol. And here we are providing some more quantitative information to take those decisions. We are not at the level of the second decimal digit, or the first decimal digit, not even the first decimal digit sometimes. But we are certainly more informative than just looking at qualitative behavior and decided on the basis of the statistics or the, say, proper experience. But this is a mathematical issue, which is very important, of course.
So thanks a lot for the beautiful talk. So I would like to ask, let's say, a general question. So we know that modeling the whole cardiac dynamics is extremely difficult, and any model has some limitation. So I would like to ask you, so what do you think are the limitations, not your model, but in general, let's say, of state, so the limitations of state-of-the-art cardiac modeling? And so among these limitations, what are the ones that you believe can be solved, overcome in the next future? And what are the ones that you think are, let's say, impossible or will be solved in a, let's say, larger time scale? And then I have a second question, more particular. So I saw that from your fluid mechanics slide that you are using a large eddy simulation approach. So the question is, why not solve indirectly the Navier-Stokes equation?
Well, I start from the very last one, because it's very easy to say, why not? Because you're solving it in general geometries with tetrahedra, with meshes that are extremely fine, and we're not able to solve by direct numerical simulation those type of problems. Maybe you can help, but we're not able to use that numerical simulation in this specific context in moving grids. So that's why we're using large eddy simulation with variational multiscale. But I mean, this is one of the limitations. Now, perhaps the most important limitation is the fact that even though this model is very general, we say holistic, is not general enough. For instance, it's not connected to the nervous system that generates the impulse, the electrical impulse. It's not connected with the metabolic response, right? So what I like to do is to put also this element into the picture, of course, in a synthetic way, say using zero-dimensional models for both these, but some interference with this, sorry. So even though it's very general, it's not general enough, because we miss some very important components. And somehow we have to deal with that. But sticking with the actual model, I think what is very important is we have seen remarkable improvements in improving the generation of the active force at the cell level. This is the real trigger, right? And this is yet phenomenological. We have to learn a lot there on the ionic activity, using the right ionic model and using the right active force generator to improve the whole thing. This is one issue. Then, mechanical constitutive laws. We're using a hyperelastic with orthotropic laws. There's still a lot of room for improvement there, I think. I'm relatively confident with the fluid flow, even though we're not dealing as you do actually with the numerical simulation. Valves, extremely important. I mean, the effect that the valves have on the fluid are extremely important. So as you have seen, we are not simulating the mechanics of the valve. We are not using three-dimensional models of the valve. We are simulating their presence and the effect on the fluid. And still, you see that there is a lot of room for improvement. And finally, well, finally, there are many finalists actually here, but let me just mention one. In pathological cases, you know very little. I mean, medical doctors can help, but up to a certain level, you know very little about the actual, say, element factors or parameters that characterize pathological events. So there's plenty of room for that to improve. And there is where I believe that interplay with data-driven models can actually help. And I'm confident that even though we're moving in a world of scarcity of data, I'm optimistic and believe that will be more and more capable of generating at the world level databases of solutions that might help to fit in a better way new neural networks.
I have just a curiosity, a mathematical curiosity. When you do the time integration, when you simulate a heartbeat, the time stepping is uniform or the step is variable?
Okay.
Because from adaptivity of the step size, one could have in principle a significant gain,
Yeah.
in my opinion.
So what we are doing right now is to split every second, every heartbeat in at least 1,000 of substeps. At least. We use uniform. We also use a certain time non-uniform. So it could be 1,000 or 1/10,000, depending upon the accuracy that you want to achieve. First of all, we use second order method in time. We could do better, but already second order. We used also non-uniforms, because if you look at the action potential, you see that you have a very strong
Exactly. This was
depolarization.
the reason of my question.
So you can also use non-uniform at the beginning, but imposed is not adaptivity based on the receiver, because this would be too costly. So it's always a compromise between the accuracy that you want to achieve and the complexity. But using adaptivity, the very first, or say different time step, this is important. And there is another point that I didn't mention. We use different time steps for the different processes. So we use, roughly speaking, 10 to the power minus 4 for the electrophysiology and 10 to the power minus 3 for the mechanics and for Navier-Stokes. We use a staggered approach to allow for this type of difference.
I see.
Because the characteristic times of the different physical actions are different.
Thank you very much. So if there are no other questions in the floor outside here, now there is a coffee break or refreshments, and of course you are all invited. And we thank again Alfio.
Thank you
for
for your
very
questions.